Thus far, we've only been talking about seeing things that our eyes can see in terms of the electromagnetic spectrum of the things that we can see. Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Today, what I want to talk about is seeing things that our eyes can't see. If you remember in the previous chapter, we learned about infrared and ultraviolet and the different types of light. Well, we can look at space at different wavelengths of light. Now, we can't see them, but we have detectors that can see them. So let's talk about that right now, okay? So, many astronomical objects radiate wavelengths that are not visible. That means our eyes cannot see them. All right, for example, cold gas clouds, they radiate the radio waves. Dust clouds radiate in the infrared, and hot gases and black holes around the black holes, emit X-rays. Some of these pictures that we see are some of the most stunning pictures maybe ever taken from the sky. But guess what? These pictures are not real in a sense. I mean, they are real and they are real events, but they are taken in non-visible wavelengths. And then what we do is we have what we call false color images. So we've put colors to them so that our eyeballs can see, and so they would look like this. But we're looking at radio waves and infrared, things that our eyes can't see. So they've been recolored so that we can look at them. Okay. Again, all right. So let's talk about radio observatories. Now, you look at these things right here. These just look like big satellite dishes, don't they? But they're pointed up at the sky, and you can collect radio waves from space. And so this right here, this array of which looks like a bunch of different satellite dishes, are collecting radio waves from space. And they're all spread apart. They're kind of that interferometer concept that we talked about earlier. This is considered essentially one telescope, and these are their mirrors, if you will. And then you've got the detector right there. And the detector is detecting radio waves. All right, and you can get big ones, 10.4 meters in this particular example here, and but you can put them all together and you get a huge, if you will, telescope. In fact, some radio telescopes will span the size of almost of the Earth, and they can be connected together via computers. And then you can see some amazing pictures, so to speak. You can't really see the pictures because our eyes can't see in the radio range, but we can false color them. Okay, here's some pictures from radio waves. Okay, false color images are typically used to depict wavelength distributions in non-visible observatories. What I mean by a false color image is that we say, all right, if it's closer to one wavelength, it'll be a red versus a blue one, and then we can kind of see what it would, so to speak, look like by having what's our false color. So for particular wavelengths, they've made it red, another one blue. They aren't really red or blue. They are in the radio wave, so you can't really say there's a color to it, okay? But there's a wavelength to it. All right, for example, gamma ray bursts, okay? This is something that scientists are wanting to explore right now, new wavelengths, which are gamma rays. Well, gamma ray astronomy began in 1965, and by the 70s, gamma rays found to become familiar objects, the Milky Way center and remnants of exploded stars. So when they started looking at gamma rays, remember gamma rays on the electromagnetic spectrum are the most intense of them all. Gamma rays are right here, and then we have X-rays, and then we have ultraviolet, UV that says, and then we have right here the visible light, that's what we can see, and then infrared, microwave, and MW, microwave, and then radio. This is visible right here. So gamma rays, we find this in exploded stars. So if we can essentially point our telescopes up at the sky, and that can collect gamma rays, then we can see new stuff. And so that's kind of the idea. Okay, in '67, from space, were discovered by military satellites watching the Soviet nuclear bomb explosions. We said, oh, we can kind of see that. They were looking for like nuclear bomb stuff, and they found stuff in space. And they think it's due to neutron stars colliding. So some cool stuff that was discovered there. All right, now just real quickly, you don't need to copy this, start down, but I think it's just intriguing how gamma ray bursts kind of led to us understanding something called the Crab Nebula. In 1054, ancient Chinese noticed a bright new star in the sky, which faded from view in just over a year. And then 1731, with the help of the telescope, a fuzzy patch was discovered in the area of the former new star. So you had the star that appeared, and then it went away. But in 1731, we got a new telescope. We pointed it at that star, and we saw some stuff there. So it was kind of a fuzzy patch. In 1844, they were noticed that they gave a fuzzy nebula the appearance of a crab. Oh, it's kind of the shape of a crab, hence the name, the Crab Nebula. In 21, the comparisons of the photographs from years and years and years led to the idea that the nebula was actually getting bigger. So at first, when they saw the nebula in 1731, maybe it was this big, and in 1921 it was bigger. And they said, oh, it's expanding, it's growing. And in 1920 it was realized that the ancient Chinese had actually observed what we call a supernova explosion, the death of a massive star. And the nebula was the result. We're going to learn more about that when we study stars, but it's kind of cool just how it was discovered. Okay? Some observations of this nebula. In 28, the crab has been investigated at all the wavelengths. So now let's talk about non-visible wavelengths. First of all, when they pointed radio telescopes up there, they discovered it was a very powerful source of radio waves. So, and this is a picture of the Crab Nebula. It's a false color picture. No, actually, that's probably a real color picture. Further radio observations reveal the remnant of a supernova explosion in a rapidly spinning star 30 times per second. Okay, and then radio waves were also indicated that charged particles were moving at near the speed of light. So they found some particles that were just moving really, really fast, close to the speed of light. And that says, something's happening. So this is a big explosion. So this is the remnants of a supernova. All right, and then visible light indicates an expansion of the nebula at about 1,000 kilometers per second. So with visible light, we can actually figure out it's moving apart. It's growing, and it's growing at 1,000 meters per second. And it's also a huge source of X-rays. So they have made observations of all the different wavelengths, at X-ray and radio wave and all this kind of stuff. So it's pretty cool. Okay, so that's just quick. I thought it would be interesting to go through and talk about the Crab Nebula because we were able to explore it at various different wavelengths. So that's the end of another quick podcast.